so let me talk about that. So things we need from last class. Maybe it's the last few classes, I don't know. Okay, so just to remind ourselves what we're doing, we've developed this functional integral for the partition function. And the mean field theory that we've been essentially working on exclusively is just a saddle point approximation. And we derived an expression for the two-point correlation function for the Ising model. And then we looked at the case where T is greater than Tc. So in the mean field theory, the magnetization is strictly 0. And then we got some expression, which I'm going to use today. So I wrote this, but then I didn't use it last time. Okay. T greater than Tc, so that big M, that mean field magnetization is 0. Then I use the Fourier transform. To get an expression in terms of momentum. It's 1 over T, that's beta JQ. And that's where I started discussing, series of approximations. One of them was that we're in the long wavelength limit and the wave vector is much longer than the interaction range. So then we expanded out J of Q. So see, J of Q was expanded. And this kappa, we're actually going to use today. Okay, so that gave us the Q dependence. That's the important part of the two-point correlation function. And so again, using a Fourier transform, I derived the expression for the correlation length. I wrote this last time, but I got it wrong because I was guessing. So I had a 2 here instead of a 1, right? So now this one should make sense, because in 3D, 3 space, we're only talking about spatial dimensions here. So then you'll get the same form as you got for the 3D integral that we did. So that assignment 1, or so question 1 on that assignment, you're doing the general dimensional integral to get this form here. So that's homework number 2. Okay, everything clear up to this point? So what we're going to start doing is moving away from the mean field description. And what we're going to talk about today is like how you do this, and the sort of the strategy, by which you would start to put in fluctuation corrections to this. Okay. And I mean, you have this functional integral formulation at the top, and we've already shown that it's equivalent to this phenomenological Landau mean field theory, whatever you want to call it. So we're really throwing out a whole bunch of the power of the functional integral, or so you imagine. And so what we're going to explore today is how I would put fluctuations back into that functional integral. So we're going to look at how we might, perturbatively putting fluctuation corrections into the mean field solutions. And it's okay to look at steps here and wonder if they make sense, because one of the lessons that we're showing here is that this doesn't necessarily make sense. And the breakdown of Landau theory corrected by fluctuations is the reason that we have to develop the renormalization group. And basically the reason that this approach, which I'm going to spend the whole entire class on, breaks down is because of the fact that the correlation length, as defined here, diverges. So that divergence makes your fluctuations in this treatment diverge. And so what I'm doing is building a framework. So I'm just giving you the punchline, where I have a correction, right? So it's a subleading correction to some mean field theory behavior. But what we're going to show is that that correction is larger than the leading order behavior. And it implies that all the subleading corrections past that, qualitatively would change the behavior of the mean field theory. And that basically tells you that it's not working. So you should be thinking, how would you do this? Well, you have an action there. You have a mean field solution to that action. So if you imagine that you're essentially at the mean field phi bar, so you're near the minimum of that free energy functional, the typical way that you would put in fluctuations would be to somehow Taylor expand that so that you're capturing, motion, if you will, around that minimum. And that's, if you develop classical mechanics and you have a potential or something like that, that's the way you do it, right? You do a Taylor expansion, and then you consider higher order terms. So for us, the object we have is that action. So functional integral. So that's the mean field phi bar. So S okay, so I need higher order derivatives with respect to or evaluated, if you will, at that mean field. So what about the first order correction? It's 0 because we're at that minimum, right? So all we have to deal with is this second order term. So we need two partials, right, with respect to two different field values. Phi equals phi bar delta. Let me forget this bracket. I'll explain what this is in a minute. So 1 phi. Let me write it like that. And so delta phi, say I, It's just the variation or the difference between the actual field value and that mean field that we're sort of expanding around. So it's just minus phi bar. Okay, and the linear term is 0. We're expanding around the minimum.
Instead of phi I bar.
Yep. Thanks. In the mean field, it's all uniform, so phi I bar will be phi. Okay, so the action that we're going to use is the mean field action. We've already taken the trace. So, the first thing, which may or may not make sense, is we're taking the saddle point. Okay, so we can solve the action at that minimum because that's by extracting it from the functional integral. That's what allowed us to do the trace. So it's that object that we'll basically take the derivatives of. So we've seen this before. Yeah, we'll do it like this. J. Right, so remember we had a term that we took the trace over the sigma variables. So that's log or ln. And it gave us this hyperbolic cosh, and I don't need the on-site field. I think that's right. Okay, so now we can imagine taking derivatives with respect to the field. And let me do it. Let me rewrite this so that I'm writing things in terms of this variation, a delta phi. So I just substitute phi I here and phi j, right? So it's phi I minus delta phi. Plus here. That's I, that's j, minus ln. Okay, something like that. Okay, just substitute that in. And I need the second derivative term. So now I need this piece. And I'll do it in 2 steps. So it's 1/2 out front, but so I can take a derivative of s, partial derivative of s with respect to phi I first. We've done this one before. If you look back in your notes. Because this happens to be hyperbolic tangent. So that's where your mean field magnetization equation came from, remember? You're minimizing this equation. So we've already done that one. And so we just need to take a second derivative. I can probably fit that on the board. So the second derivative. Now we have with respect to J. Because this piece only has one field in it. Right, and we're picking out a field index here, J. So that sum of all those sums, all those elements of that sum, only one contributes. So we're just left with the inverse interaction matrix. Then for the second term, we get tan h squared phi I over t. Yeah. Okay, so now let's evaluate at phi equals phi bar and put into that expression. We need a 1/2 in front of it. Ij. Is this a 2? I don't know. Oh yeah, God, I need that. I just wrote this again for nothing because I need these here. Okay. Let me just write it like this. I have a I and a j index here. There's my first term. Minus 1/2t squared. 1 minus tan h squared. I'm evaluating at phi equals phi bar. So whenever I see this field, let me just put it in phi bar. Oh. And my sum over ij in the two fields. Right, so you just inherit that sum and these two variations of the field away from the mean field value. And you're evaluating at phi equals phi bar. Okay, so it could be simpler. We have the fluctuations now, in some sense, here and here. This piece here doesn't have the fluctuations in it. This is just like the mean field magnetization squared. So we can substitute that in. Let's see. Why not? That gives us a pretty nice simplification. Let's write the whole S. And I can get rid of that T by using the mean field solution. No, let me think about that for a minute. I can use T equals J, but I have to be at TC for that one. Let me put J for now. I'm not sure that matters. I have two fields here. Okay, I have some term which somehow I'm going to throw away soon, I think. I get the feeling it's not going to be around much longer. This, I have one index here over that field left, right? I just have two independent sums, basically. So I can write this with a delta function. And then this can be evaluated, but we have to use some matrix methods. So it's simpler to just write that, this piece and this piece as a matrix and try to combine things into one, one set of fluctuating fields. So let me define a new matrix. I'm going to call it A. And that should simplify our notation. So A is going to be, see, I need 1 over T. So I'm going to pull out the J inverse. Then I need 1 over T squared and a delta here. So if I do that, then I have a 1/2. Yeah, I think that works. Right. Okay, so then so I want something that looks like, yeah, I can do a Hubbard-Stratanovich on this. Okay, good. So I'm just trying to write this like a Gaussian integral because it's the only way you can solve things. So what does that mean? That means our full partition function, which I've written up there. So the functional integral. So I'm putting this back in the functional integral, but I have a action, right, which is sort of mean field plus fluctuations here. So I don't know, this, okay, so I guess this is only approximately equal to this, right? If I use the same, I haven't labeled this thing, but this is the truncated Taylor expansion, if you will. Right, so that'll give us this piece out front. And then the functional integral, I can write it as d delta phi, because all of the additional pieces that affect the Jacobian are going to be these mean field values, which are just the constant values. So I can write the functional integral like this, and then just that nice Gaussian piece, J, Ij. So when you see this, just remember the Hubbard-Stratanovich transformation. It was always written in terms of the fields phi, e to the minus 1/2. So I've used this A notation on purpose. What you had in the Hubbard-Stratonovich transformation was an auxiliary field that coupled phi I and sigma, no, what is this, gamma? And then this thing was equal to 1 over the root of that determinant. And then you had a piece that just depended on the auxiliary fields. And the inverse matrix. So what is this equal to? Well, it looks exactly like this with an auxiliary field, if you want to call it that, set to 0, right? So then this piece just turns into unity. So it's only a root, 1 over root determinant and a constant. So it's just the usual Gaussian integration. Just set phi I equals 0. So your partition function is related to the root of that determinant. So let me just call it C, because nobody cares about that piece. Let's be careful with that piece. And then we just have, right, basically mean field solution. And C will be ignored. We always ignore constants in front of the partition function because almost exclusively you're interested in maybe ratios of partition functions and stuff like that, derivatives. Okay? So I'm going to rewrite let's look at the free energy. That constant, if you calculate the free energy, becomes an additive constant. Another reason we don't care about it. So there's a mean field piece. You're taking a log, which is the mean field piece is just the action evaluated with the saddle point approximation. Okay, so we already know what that is. Let me just call it that. But we're interested in corrections. Okay, so I need, it's 1 over square root, so it's plus 1/2 log. Oh yeah, my t's here. Okay, t log, and then the determinant of A. Okay, so we need to handle this thing somehow. And the easiest way to do that is to just use a matrix identity. So let me write that first, then I'll sketch a quick proof. So log determinant of a matrix is going to be trace of log of the matrix. Has anyone seen that before? Is that fairly standard? Do you need me to prove that? I don't know where I saw it. I can sketch out a quick proof. Oh, I started doing it right before class. I got interrupted, so I don't know if it'll actually work. But let me just show you how roughly this comes about.
That's just from diagonalizing it, isn't it?
Yeah, if you just write it as a diagonal matrix. So let me just see if I can fit it in here. You can do it in the continuum, or you can just do it with matrix. So if you write a matrix, I did it backwards, but that's orthogonal in our case, an orthogonal matrix. Then just calculate the determinant of A and because this is distributive and the determinant of U, any orthogonal is either plus or minus 1. So you can write it somehow like this, probably. Pardon? Oh yeah, God. Don't get that. Actually, they look too similar. Then really you're just dealing with the determinant of A, of lambda. Okay? So maybe you already knew that. Now you need a function in the next step of the proof. So any function of A is diagonalizable. You can just write f of A f lambda and then calculate the trace. So that's like the left hand and right hand side? Left hand side. Let's calculate the trace of that function. Okay, so just really sketchy. So trace of, let me call it function of A. The trace is cyclic. So somehow you can get these two together, presumably like that. So now you just have trace of a function of a diagonal matrix, because this gives you the identity. So this will give you the trace of f of A. So this should give you the product over all the the product of the eigenvalues, so the diagonal matrix elements. So I'll call them lambda. Because all you have to do is relate these two steps. Do you need more? Another line? Can I write it here? So what you need is trace of log A. So f is your log, which is just going to be sum. All it's going to do is basically turn this into a sum, right? And then you need the determinant of A. Oh, and you already know that that's product, right? So the determinant of A is just, sorry, did I get the sum and the product mixed up? This one's the sum here, sorry. This one's the product. And it's A, so it's just lambda alpha. Okay, so if you just take the log of this, then you see it turns into the sum, right? That's as much proof as I'm going to do. So we're using this, and we're going to substitute that into our expression for the free energy. So we have a mean field piece. but we're interested in the fluctuations, so that's going to be 1/2 temperature trace log of A, the matrix A. So I have my A somewhere. So I got my A up there. Let me look at that. Okay, so I'm just basically factoring out a JI, say L. I'm writing a sum over L. LJ in this case. That's the inverse matrix, but I've summed over an L here, and I have an identity for this piece. And let me redefine A is the part in the curly brackets. You call it B or something, but call it A tilde. So in matrix notation, without these indices, what do I have? A is 1/T, A tilde, J inverse. So I can rewrite my free energy. Log of A is log of this thing. Okay, so we're still chasing that fluctuation piece. So mean field plus 1/2 T times trace log 1/T A tilde J minus 1. Maybe? And that log helps us out. So which of these two terms is important? This is like the inverse interaction matrix, in some sense. Where's all the singularities? We're trying to chase singularities in these expressions. Right, so A has pieces which are proportional to, fields. J's and temperatures. This thing here is just an interaction and a temperature. As we approach a critical point, the only thing that happens here is this goes to TC, right? And this thing doesn't change at all. So there's got to be nothing interesting in this second piece. So even if we're not sure about this piece, definitely this piece is nothing interesting in it. Nothing's blowing up as T goes to TC or anything like that, right? Let's just throw it away. Why not? So we're approximating, you know, a free energy, which is a mean field piece, plus a fluctuation piece. But we're really only evaluating it, you know, for the singularity structures that come from fluctuations, or to determine how maybe fluctuations affect the mean field theory. So keep that in mind. So we'll look at a specific case. So now we have a free energy. We can evaluate the free energy above or below the transition temperature in the same way that we did before. Above, we can set the magnetization to 0. Below, we can't. So I always do above in class because it's easier. And then from that free energy, we can calculate a susceptibility or an order parameter or a specific heat or whatever, right? So that's all we've done now. We've just set this up so that we can calculate a physical observable. So let's calculate the specific heat, say. And let's look at how the fluctuations from that second term affect, you know, the critical exponents, the universal behavior, or the divergences or whatever associated with criticality. So again, what we're somehow believing, or we're hoping, is that we have a universal number. We have a critical theory with universal numbers. We have a mean field approximation of these, 1/2, 1, whatever they are. And we're hoping that when we add fluctuations in, the fluctuations just give us like, you know, it's going to be 1/2 plus some small number plus some smaller number if you had the higher order terms. And so you just kind of like converge on some you know, more accurate value for the critical exponents. But what we're going to find is that that second term in the free energy gives us additional divergences. And so that is the problem with doing this. So if along any part of, you know, when you set up the problem, you know, at the start of class, and you wondered if that's the right way to set it up, this is going to tell you that it was the wrong way to set it up. But this is the way you would do it naturally, is by doing this in an analogy to a perturbation theory. So let's look at and that thing I wrote at the start of class. I can write this in terms of a 2-point correlation function. So bear with me for a couple steps here. So this is the right equation for M, big M, or phi bar equals 0. GLJ. AIJ tilde. It's almost like all that time ago, I knew what I was doing. Because AIJ tilde is just this piece now. It seems implausible that I knew that I was what I was doing. This must be Anton's notes. He would definitely do this. So remember, this was like almost, I don't know if this was last lecture or the lecture before, right? But since we've, actually I didn't say this before, but since you have a sum over this L index, GLJ, this is just the inverse of this matrix here. This happens to be the 2-point correlation function, but so you can also write this sum over L. So I have LJ there, so I need IL inverse GLJ. So that means that my A tilde is just this inverse correlation function. I'm going to write Jij because phi bar is 0. Yeah. So then that's just this term here, which I'm going to call Gi, and it has to be J inverse. So again, this is general, except I've thrown out this piece with no singularities. Now I've specialized it to t greater than Tc. So in that case, then I can write the free energy as the mean field piece. Okay, I'm sick of writing that, so let me call it delta F. Where delta F is just 1/2 T trace log of G inverse. So let's leave the free theory, the mean field piece alone. And let's just calculate delta F. And in order to do that, I need to diagonalize. No, I need to take the Fourier transform into momentum space again. So let me do one more step. So momentum space, we just throw this in the Fourier transform. So let me do it like this. This is what I want to replace. Oh, maybe I want the inverse, G inverse. Doesn't matter, it's just another matrix, right? So I have a trace. Okay, so I'm not going to do this. I'm not going to do this again because I think it's just confusing. But if you just note that you can write the trace it's going to be trace, let me just call it A, as a sum over two indices, but with a delta function. then you can easily take this Fourier transform and show that I should get something like 1/2 t. So that delta is going to take care of the sum and leave me with an index. And I need the inverse q. Okay, so convince yourself of that step, much like my convincing proof here. And let's take that and calculate some corrections to it. So let me, do you know what inverse G is, right? It should be related to J. Something I wrote at the start of class, I think. Okay, well, it's up there. So it's delta. So alternatively, you can write this. I'm not sure which I want to use. Okay, so let's do the specific heat. So remember, in mean field theory, the specific heat had this weird exponent alpha equals 0. And alpha equals 0 came from the fact that there was just a discontinuity. There's no divergence. So let's so CV went as 3/2. If you approach the critical temperature from below, so T goes to TC minus, and then at a discontinuity, if you were above TC, say. So anywhere above TC, you have a discontinuity. So that made us write this as T minus, so the reduced temperature, T minus TC. Then we defined an exponent where alpha was 0. Okay, so that's the crummy case that basically didn't have an exponent. So you want to believe somehow that fluctuations, okay, we have this discontinuity, fluctuations should give us small changes to this discontinuity. So remember, in order to calculate the specific heat, we take the second derivative of the free energy. So we're just going to look at the correction. So we take the second derivative of delta F. Okay, so how does that look? So let's call it delta CV, I guess. Minus 1 over n T, second derivative of delta F. Sure, why not? Over T squared. Okay, let's use J of Q. Remember, I expanded it out in terms of 1 minus 1/2 or something kappa Q squared. So the Q dependence of this whole thing will be contained in that object. So let's take the first derivative of delta F. So the T comes out 2T squared J of Q 1 minus 1 over t. Okay, so we're lined up for a fairly unpleasant second derivative. No sense procrastinating. Okay, so we have t dependence here. Again, so that'll give us j of q. We have a t dependence here. Let me just get rid of that. Over t squared q. Right. And the last piece we have to take the derivative of gives a minus sign. Right? Then that piece has to be squared on the bottom, 1 minus 1 over t jq. That all squared. If I did this right, then the first two terms will cancel. Sure, I'm going to say yes. So this one cancels this one. By a miracle, it's not going to look so bad. Okay, so our delta CV sum over Q. So it's fairly general in terms of J of Q. You know, all we've done is, well, we've done several things. We've thrown away this non-singular piece. We're looking above the transition temperature. Okay, so that eliminates the phi bar. We've written this in terms of J of Q. We can expand J of Q now if we're interested in the long wavelength limit. And we know that expression from last time. So that's JQ is approximately equal to some constant minus this thing kappa. And since we're now isolating Q as a variable, we'll take this sum and we'll do the calculation in the continuum. So we'll take the thermodynamic limit and change that sum to an integral. So by the formula, by the logic last time, let's do this in d dimensions, if I can. So it's L to the d. That's the size of a unit cube. dq. And I think this, you define, again, L to the d over n is the lattice constant, a raised to the power of the dimension. So then our integral goes over the Brouillon zone, minus pi over a to pi over a. I have a d-dimensional integral. Then I have j over t from this piece squared. I'll just write it like this, and 1 minus j over t q squared, all squared. Okay, so I've made an approximation. Here, so we have the first contribution to that integral. 1 over j, so this part here plus is important, plus 1 over kappa, then I have t, everything squared, right? Okay, so that's a leading order behavior. So all we're doing is analyzing this now. Okay, so I've just written a integral expression for the fluctuation correction to the specific heat. And I can just end class now. You can just take this integral and start analyzing this and tell me what you see in it, right? So let me help you. So what do you see in an integral like that? There's cases when that integral is going to converge to a number, say. And there's possibly cases where it's not. And that depends on dimension. So the dimension matters quite a bit. And the dimension affects that integral because that dq, that integration variable, right? You can imagine writing this in spherical polar coordinates and momentum space. And you'll see how q scalar dependence drops out. So in order to do that, let me just rewrite this. So I'm just going to rescale this integral now into successive forms that we can analyze the convergence properties of that integral. So let me change variables. I just want to take away the unit. I want to define a dimensionless momentum. Okay, and I do that. I can do that by defining another momentum, which is q times a. So the dimensions are contained in that lattice unit, right? How many angstroms, between each, say, site on your lattice, on your hypercube. So let me call this a dimensionless big Q. So I just want to rewrite that integral in terms of that. So I'm going from minus pi to pi. Q squared over a squared. So I do that at the price of an a there. Let me think. Pull out part of this numerator. So let me worry about this d-dimensional integration variable in a minute. J over t squared. Let me pull out 2ta squared over kappa. Pull that out on top squared, which gives me Too many steps, maybe? So I have T minus TC from this, T minus TC, kappa. Okay, so I've used the J, the mean field solution. Q squared, okay. So I've done that now so I can write this in terms of a correlation length. Because we remember how we define the correlation length, which I might have forgot to do at the start of class, but remember, square root T minus DC. So that correlation length is basically occurring in there. It's squared, and A squared is also occurring to keep it dimensionless. So let me call that a kappa. I have T squared to cancel. Then I have Q squared plus, so it's say A over Z squared. So we're in a pretty good position here. I just want to be careful with dimensions. I have kappa here. I have this lattice spacing, which has a dimension. So let me just look at that kappa real briefly. So we already know this, but great, so I have one sum here, which means I've taken a sum, I, and that's what I've defined as J, remember? And so my kappa Ri minus Rj. I wrote that at the start of class. Okay, so I have ND, and then I have essentially a Jij, and then, you know, the distance, the scalar distance between those two sites. So just like I did last time, let me make an assumption about the range of this interaction. So let me define dk over j, right? And let me call that r squared. And I'll call that, that's just some sort of almost phenomenological range. And we're just introducing it so that we can say, so for example, the correlation length is greater than or less than the range of the interactions. So you can imagine a nearest neighbor, Hamiltonian. You know, the range of the interaction is just nearest neighbor. Could be A in that case. So you can imagine the range in very simple models as just being 1 or A, range over A, being 1. But what I'm saying is also true when you have more complicated interactions. As long as you can define a range. What happens if they're infinite range? We already solved that problem, right? If they're infinite range, you know that you get the mean field solutions back. So this is just a mechanism of saying, you're between something that's nearest neighbor and maybe something that's, you know, infinite range. So even if you have a long range, but you have some sort of decay of interactions, you can still define limits, you know, correlation length much greater than or correlation length much less than. Okay, so then my delta CV. Okay, so all I've done is simplify. Oh my God. That expression. So you have a over r to the r, be 4 out front. And then just that integral that has different convergence properties depending on dimension. So let's finish up by analyzing that a little bit. So we want to analyze that integral. Say, the simplest case to do it is when you're exactly at the critical point. When you're exactly at the critical point, you know that that correlation length diverges. So it's like we're approaching TC from above. Now we're exactly at it. So this one's simple. I have A over Z goes to infinity. No, goes to 0. So my delta CV, 2D squared. Yep, A over R to the 4. And then my integral is just one over Q squared squared. Okay, that one, now you can see very simply the structure. There's no angular dependence of anything in this integral. That's assuming some symmetries. So if you assume, you know, translation CV4 or whatever it's called, inversion symmetries and so on, what you're doing in the continuum in momentum space is throwing out all the angular dependence of this integral. So you can evaluate that integral without any thetas or phis. Angular. This is the most useful thing in the world. dq, okay, the integration variable, is just, as you know, q to the d minus 1, and this piece here, that I've called S, it's just the surface area of the sphere in, you know, in unit radius, a sphere of unit radius. So this expression is, I think, this in d dimensions, gamma d over 2. Yeah, that's really useful. I love this. So you just pull this piece out. This gamma function just depends on what dimension you're in. And then the only part of this integral that matters is how this and this interplay, right? Just generally useful. So now you can play around with dimension. And so let's do 3 dimensions. You know what this is, SD. You can check it. 2 pi to the 3/2, gamma 3/2. Then in 3D, the fluctuation part of the specific heat. I just wrote my 2 expressions backwards, but I just wrote the general expression. I'm not going to erase it now. Okay, let's look at the general expression. So it's all about the convergence of this integral. So when d is less than 4, less than or equal to 4, so when it's greater than 4, that's the only time it converges, right? So that's basically the lesson. I mean, what we're doing was we have a mean field value, or mean field behavior. The specific heat goes to 3/2, has a discontinuity, goes to 0. And again, we're looking at the fluctuation corrections to this. The fluctuation correction to this has an integral that diverges for d less than or equal to 4, right? So a divergent contribution of the specific heat for d less than 4 means that you basically have a problem with mean field theory plus fluctuations. The whole framework, like everything we did today, is wrong. That's what this is saying. You gotta be a bit careful if d equals to 4. We'll talk about that then. They call this the infrared divergence sometimes. So fluctuation contributions. Fluctuation contribution to mean field theory is qualitatively wrong. So I mean that, again, you had some behavior in the mean field case for the specific heat near TC. And it was like 3/2 and then a discontinuity. So now what you're seeing is in dimensions greater than 4, you get some convergent integral, and so basically you get some fluctuation corrections. So you'll get something that changes this, who knows how, but mean field theory is qualitatively correct when that integral is well behaved. But for d less than 4, so this is your mean field. This is your mean field theory. And then your fluctuation correction looks, I don't know, something like this. Plus delta, I don't know, delta, whatever, phi. So we're going to continue with this and explore, I think, a bit more, or analyze a bit more of the structure of this integral as we go on. And another important point is that this divergent structure, essentially this integral over big Q, will occur in the fluctuation corrections to any other quantity, like magnetization or susceptibility or something like that. So even though I just did this specific case of the specific heat, this idea that you have a breakdown of the theory would occur if I did any other quantity. It comes from the fact that I'm taking derivatives of this free energy to define thermodynamic quantities, right? So basically from this type of step here, you can just follow things along for other quantities and get this type of integral and analyze its behavior. So try the susceptibility. If your assignment's too easy, you can do that as an exercise. So the role of 4 dimensions, this is where we're seeing it's coming out as being special. So next class, I'm just going to talk a bit about this Ginzburg criterion for when mean field theory is valid, if you want to call it that. And then what we're going to do is look at this breakdown of Landau plus fluctuations in the phenomenological theory. Very similar in many ways, but we just want to talk about the general structure of, say, these actions, of the functional integral for phenomenological or more generalized Landau theory. We'll do dimensional analysis on it. And so the point is we're just going to explore this breakdown a little bit more to motivate, the idea of scaling and renormalization group. So we should start to get to that in maybe 2 lectures or something like that. Okay, so we're almost done the sort of preliminary work to start thinking about the RG. Okay, so give me your assignments, and you have your assignment 2, which is due in 2 weeks. And I'll see you guys next, Wednesday.